A lot of times we will use the power spectrum as a way to represent what's going on with our signal. Basically, the power spectrum is defined as the Fourier transform of the autocorrelation function. So in this equation, the autocorrelation function is given by Rxx. This is the continuous Fourier transform representation. This is the discrete representation. So basically, we're taking the discrete Fourier transform of the autocorrelation function, where autocorrelation was defined in a previous set of lectures. So this gives the power spectrum. Now, the autocorrelation function has even symmetry. So because it has even symmetry, if we were looking at the Fourier series as sines and cosines, we would not have to include the sine terms because they're odd. And given the even symmetry, the odd terms would cancel out. So we can actually take this as cosine transforms. So this is actually the power spectrum given as a cosine transform of the autocorrelation. So we can have a more direct approach if x of f is the Fourier transform as a function of f. The power spectrum is basically the magnitude of the Fourier transform squared, and this is probably the one that you're more familiar with. Now, the power spectrum doesn't contain phase information, so it's not a reversible transform. You can't, it's not a bilateral transform. You can't take the power spectrum and ever get the original signal back. So it's usually applied in situations where phase is not considered useful. So as an example here, determine and plot the power spectrum of heart rate variability during both a normal and a meditative state. The power spectrum can be determined through the Fourier transform using the direct method. You take your heart rate data and first convert it to evenly sampled time data. In this particular case, the data set's providing the heart rate at an unevenly spaced sample rate where the sample times are provided as a second vector. So those need to be rearranged into evenly spaced time positions. So basically what's done is the data are resampled. Now this is actually fairly common, and it's not so much common as in this example, but it's common when you have two different data sets and they're sampled at different rates and you're trying to do something like correlation or cross-correlation between them. And so it's important that the sampling times are the same. So it's not uncommon to have to do an interpolation routine. Interp 1 takes those unevenly spaced pairs and creates basically an evenly spaced data set in the time domain. So I'm not too concerned about figuring that out right now. Let's just say that we take the result and look at what happens with the output, which is basically little y. So we have our resampled data set, and now we're going to take the direct approach to plotting the power spectrum. So the comparison is on the left we have just normal heart rate variability, and on the right we have that heart rate variability during meditation. So what we're looking at is there's a big peak here when people are meditating with their heart rate variability. It corresponds to about 0.12 hertz or 8 seconds. So something is going on during meditation with the heart rate variability. It's fairly low under normal cases and then increases with frequency during meditation. So just like we can average time signals, we can average power spectrum as well. Even if we have only one signal, we can take segments of the data and use averaging. So the power spectrum determined from each segment is used to produce a spectrum that better represents the broad or the global features of the spectrum. This is popular when the waveform is just a sample of a longer signal, and spectral analysis can only estimate the real spectrum. When the power spectrum is based on a direct application of the Fourier transform, followed by averaging, it's referred to as an averaged periodogram. So here's an example of the Welsh method of spectral averaging. Basically, we have our signal and we're going to divide it into segments. And we're going to calculate the power spectrum of each segment. And it is possible for us to have the segments overlap. In this example, we have segment 1 and then we have segment 2, and we have a 50% overlap between segment 1 and segment 2. And what we're going to do is calculate the spectrum, the power spectrum for each segment, and then average the spectra. So you can only apply spectral averaging to magnitude or power spectrum because the magnitude spectrum is insensitive to time translation, but the phase spectrum is not. Averaged periodograms usually average spectra from half overlapping segments, but it doesn't have to be half, but usually that's what you do. Since the frequency resolution is proportional to the sampling rate divided by the total number of samples, then averaging is going to be a trade-off between resolution and reliability. So every time we average, we're going to lose some resolution. So the power spectrum with averaging can be found using the P-Welsh algorithm. And the output will be the average power spectrum and a frequency vector. We can window the, we can choose to window the data. The default is hamming. We can set the number of overlapping data samples. We can set the number of data points in a segment, and we can set the sampling interval. So in example 3.7, we want to evaluate the influence of averaging the power spectrum on a signal with a combined broadband and narrowband with added noise. So this is the data file that provides the data set. It contains white noise filtered between 0 and 300 Hertz, and then it contains two closely spaced sinusoids at 390 and 410 Hertz. So here's the code, and here's the result. So here's the standard spectrum. And you can see you have this incredible frequency resolution, and of course here's all the noise. You can see that the noise gets windowed out, and then here are your two signal features. But this looks very, not only is the signal noisy, but the spectrum is noisy as well. So if we now use the averaging method, you can see that you do have this constant energy present in the white noise that does show up at approximately the noise band that we defined. And then you can see a little bit of the signal components at 390 and 410, but it's not as clean as example 3.7. So this is one of the problems with all frequency time windows being treated equally, either in the time domain or in the frequency domain. And this is one of the reasons people can be motivated to use a different kind of transform, like a wavelet transform, is the fact that you either have good resolution but poor definition, or you have, a good big picture without the fine point resolution that you might need at certain frequencies. Here's another example. Find the approximate bandwidth of this broadband signal given in this particular data set. So here's an unaveraged power spectrum of the signal. The unaveraged power spectrum is very noisy, so you can use spectral averaging to produce a cleaner spectrum. How you determine how to take the average of your spectral values is a little bit arbitrary. In this particular example, they've chosen to take the average of spectral values within 50% of the maximum value. And this is a little arbitrary, but it's just one way to do it. And sometimes you play around with this number and then just look at your results to see what seems to make the most intuitive sense. So to find the high and low cutoff frequencies, you can use MATLAB's find routine to search for the beginning and ending points that are greater than 0.5 of the bandpass value. Now remember, this is a power spectrum, so we're using 0.5 instead of 0.707, which we would use if it were simply a magnitude spectrum. So here the Welsh spectrum is taken, the bandpass Values are determined, and the bandpass characteristic is plotted. So if you look here, here is what the spectrum looks like when you use spectral averaging. Here is the location of the two cutoff frequencies. So how are those cutoff frequencies determined? Well, if you look at the maximum here, 5, we try to get like an average bandpass value, and then here is what was determined to be the appropriate cutoff values for the high and low pass. So once again, this is a little bit arbitrary. It says the window size was selected empirically to be 64 samples. What does that mean? That means they tried a bunch of different window sizes and went with the one that looked the best.